After learning this module, you will be able to know the applications of rules or theorems derived from Great Orthogonality Theorem. Learn about character tables of a point group. Know the notations followed for the irreducible representation in the character table. Know the examples, various examples for explanation. And you will also find the explanation for C3V character table. And also you will know the basis, binary and ternary basis function in this character table. Now, in earlier model on applications of Great Orthogonality Theorem, we have come across with the rules oblique theorems derived from Great Orthogonality Theorem. These rules have been explained by taking suitable examples. In this module, we will learn how to use these rules which have been derived from Great Orthogonality Theorem. In construction of character table of 5-point group. Character tables are characteristics of point group and are very useful in dealing with molecular spectroscopy and another related fields. The character table for each point group, which are generally encountered and are generally given in the end of the book on group theory. Great Orthogonality Theorem can be utilized, number 1, to find total number of irreducible representation of a point group. Number 2, characters of each of these irreducible representation. Before construction of a character table, let us see what it means and what the meaning of various terms used in this character table. What is a character table? The character table of a point group is unique, and this is the same for all molecules which belong to the same point group. For example, molecules water, H2O, SO2, pyridine, which belong to C2V point group, will have same character table of C2V point group. The general format of a character table is given as below. That is, there are A, B, C, D, E, F. 6 sections are there. Wherever you will find in character table, there are 6 basic sections. Now, different section of the character table, which have been divided into A to F section, that is 6 section, and they have the meaning as follows. Section 1, that is A, list the symbol for point group, that is symbol is Schoenflies symbol, that is C2V, C2H, D3H. So, A lists the Schoenflies symbols for the point group. Section 2, that is B, lists the symmetry operation of point group class wise. In a class wise, we list how many operations are there in a class. Section 3, that is C, lists the conventional symbol notations for various irreducible representation, and these symbols are Mulliken's symbol for irreducible representations. Section 4, that is D section, gives the character of all irreducible representation for a symmetry operation in each class of symmetry operation. Section 5, that is E, lists the basis set of representation for each of the irreducible representation. These may be XYZ axis, TX, TY, TZ translational vectors, Rx, Ry, Rz rotational vectors, or set of orbitals or bond vectors. Section C, section 6, that is F, shows that how the binary function of XYZ form the basis for representation of some of the irreducible representation. Binary and ternary combination can be x square, y square, z square, xy, xz, yz, x square minus y square, x square plus y square, x cube, and so on. These are important in dealing with the symmetries of the d or f orbital in Raman spectroscopy. Mulliken symbols used for irreducible representations have definite meaning. These will be mentioned here without going into the source of this. That is, I will not go how these symbols have been derived, but I will give the meaning of these symbols. Notation followed for irreducible representation in section C of the character table are RS Mulliken's symbols, that is RS Mulliken's notation, name of the irreducible representation. These are assigned as: number 1, all one-dimensional irreducible representations are labeled as A, capital A or capital B, as shown for C2B point character table in earlier models. That is A1, A2, B1, B2. That is capital A and capital B are used for one-dimensional irreducible representation. Second, all two-dimensional irreducible representations are labeled as E. One should not now here confuse with the symbol for identity. So, E here is two-dimensional. All three-dimensional representations are labeled as capital T or F. Usually T is used in electronic transition problems and F is used in vibrational problems. These are important in dealing with higher order representations which are represented by G, 4-dimensional, H, 5-dimensional, and so on. Number 4, for point group C infinity V and D infinity H, a different notation is used. One-dimensional irreducible representation is represented by the symbol, that is summation. Two-dimensional irreducible representation is represented by capital pi. In addition to this general symbol, most Mulliken's symbols have subscript or superscript attached to these Mullikens. For one-dimensional irreducible representation, subscript and superscripts have well-defined meaning and can be easily worked out. A one-dimensional irreducible representation is given the symbol A if it is symmetric with respect to rotation about highest order proper axis, that is the principal axis or improper axis. Symmetric means chi for this is +1. If the irreducible representation is antisymmetric, that is chi is equal to -1 with respect to principal axis of rotation Cn, it is labeled as B, as shown over here in C2B character table. A1, A2, B1, B2, that is concentration on A1, that is we take C2 axis, the character for AA is +1 and for BB it is go -1 -1. Here C2 axis is the only rotation axis. Characters for irreducible representation A1 and A2, that is A type irreducible representation chi is equal to +1, and character for irreducible representations B1 and B2, that is B type irreducible representation chi is equal to -1. For C1, Cs and Ci which do not have Cn axis, symbol A is used for one-dimensional irreducible representation, that is we have symbol A and then we will attach some G and U, that is AZ and AU if it is point group is Ci as given over here. 6a, subscript 1 is given to one dimensional irreducible representation A or B if it is symmetric with respect to rotation about C2 axis, which is perpendicular to Cn axis. Principal axis, in the absence of such C2 axis, symmetric with respect to sigma v is considered. That is, the symbol A1 or B1 are assigned if irreducible representation is antisymmetric with respect to sigma perpendicular to Cn, that is principal axis, or sigma v. The symbol used are A2 and B2. As given over here, A1 and A2 we look for sigma Vz, B1 and B2 we look again for sigma V xz over here. That is, in this we are having plus and then plus, minus 1 and minus 1. For A2 or B2, it is antisymmetric with respect to sigma V. For D2H point group, where there are 3 C2 axes and these fall in different classes, the irreducible representation in which chi for each C2 axis is plus 1 is labeled as A, while other one-dimensional irreducible representation are labeled as B. For D2D point group, the character of S2n determines the symbol for one-dimensional irreducible representation. Now, all these factors are shown into these character tables over here, which we find that these are according the statement. Point 6b, for linear molecule, the symmetric or antisymmetric in above rule, that is second A, are indicated by plus sign or minus subscript, that is summation plus or summation minus instead of A1 or A2 as shown in the table below. That is, A1 is equal to summation plus, A2 is equal to summation minus, E1 is equal to pi, E2 is equal to delta triangle, E3 is 5, and these are represented for character of E plus 1, that is A1, A2, plus 2, E1 in E2, E3 is plus 2. Like this, we have up to En. So, for linear molecules, the notation, R.S. Mulliken's notation is slightly different than the general point group systems. Point 7, subscript G, that is zeroed, or U, that is unzeroed, are given respectively to irreducible representation if these are symmetric or antisymmetric with respect to center of inversion, that is I. The symbol are AZ, BZ, AU, BU, A1U, B1U, etc. Point groups CNH, where N is even, DNH, where N is even, DND, where N is odd, OH octahedral, D infinity, all these points have center of inversion I, and there we will use AZ and AU as the subscript attached to this one-dimensional irreducible representation. Number 8, subscript single prime or double prime are given to irreducible representations which are symmetric or antisymmetric with respect to sigma h. Point group CNH, N is odd, DNH, N is odd, do not have I but have sigma h only. as shown over here. We can give the symbol as A1 dash, E dash, etc. to these various point groups depending upon the value of n. N is odd or n is even, etc. Now, in C3H character table, A1 dash is given when character for sigma h is +1, A double dash is given when the character for sigma h is -1. The rules which we have obtained, that is rule 3 and 4, are equally applicable to one-dimensional, two-dimensional and three-dimensional irreducible representation. Point number 9, if one-dimensional irreducible representation has complex character E, F or G, then there must be another equally acceptable irreducible representation with characters E star, F star, G star. These are generally bracketed together and labeled as E. In C3V character table, the meaning of the various terms and parts for the various terms in this is explained as follows. Let us now write down the complete character table for C3V point group and explain it in detail. Section A to F together with explanation is described as A. Section A, if you just look the character table, A we have written C3V point group symbol. Section B, classes of symmetry operations, that is E. Then we have C3, it has 2 operation in this class. Sigma V, it has 3 operation in this class. Section C, symbol for irreducible representations. Here, what are irreducible representations? A1, A2 and E. Section D gives the character for A1, A2 and E. For A1 it is 1, 1, 1. For A2 is equal to 1, 1 minus 1 and for E 2 minus 1 and 0. That is, this section D gives character for symmetry operations in a class. Then we have section E and F, which are the basis for representation. Section E gives the basis single, either XYZ as the basis or RXY, RX, RY, RZ as the basis, TX, TY, TZ as the basis. Now, section F gives me the binary functions or ternary functions as the basis for representation. These can be x square plus y square, it can be x square minus y square, it can be xy, it can be xz, it can be yz. So, in this we are having, that is, this is the correct table. Section A lists C3V, a symbol for point group. Section B lists 6 symmetry operations of C3V point group, which have been divided into 3 classes, that is, in E, 2C3, sigma V classes. Total symmetry operation is equal to 6, which is add H. The order of the group. Section C tells that there are only 3 classes in the group. There will be only 3 irreducible representation, namely A1, A2, that is, these are one-dimensional, and E, this is two-dimensional. A1, A2 are one-dimensional irreducible representation. Character for all matrices of symmetry operations equals to chi r is equal to +1 or -1. The A1 irreducible representation symmetric with respect to sigma V, because C2 perpendicular to C3 is not there. A2 antisymmetric with respect to sigma V. These A1 and A2 respectively are obtained when Tz or the Z and Rz are taken as the basis for representation. E is two-dimensional irreducible representation in which x and y combine together or Tx or Ty combined together, or Rx or Ry combined together have been used as the basis set for representation. In section D of the character table, list the characters of matrices for symmetry operation of a particular irreducible representation. These can be obtained by making use of the rules of great orthogonality theorem. Section E lists the basis set for representations of irreducible representation given in part C. For example, the basis for A1 is Z, and for Z or Tz, basis for A2 is Rz, and so on. Now let us try to find out the basis sets for these representation, and for this I will take the ammonia molecule which belongs to C3V point group, and let us take the Z vector along C3 axis and Rz vector also along this. These are shown in the figure below, that is in the diagram of ammonia these are shown. Let us take Z vector and see the effect of symmetry operations of C3V point group on this molecule. E operated on Z is Z, therefore chi is equal to +1. C3Z operated on Z is chi is again +1. Sigma V operated on Z, again chi character is +1. So for Z as the basis, we have character for E, C3 and sigma V as +1, +1, +1. Similarly, let us see the effect of symmetry operations of C3V point group on Rz rotational vector. These effects are given as ERZ is equal to Rz, chi is +1. C3Rz is Z, chi is equal to +1. Sigma V Rz is equal to R, that is -1. These effects can be tabulated as shown over here for A1 and A2 like this. That is, for A1 Z unit vector, and for A2 we have this vector. Z unit vector gives +1 character all symmetry operation, and this corresponds to A1 irreducible representation. Rz unit vector gives +1 character for symmetry operation E and C3, and -1 character for sigma V. These characters correspond to A2 irreducible representation. Like this, we can find out the various bases. Now let us take x and y unit vectors and see the effect of symmetry operation E, C3 and sigma V on these unit vectors. E operated on x gives x, character is +1. E operated on y gives y, character is +1. That is, matrix for E is 1, 0, 0, 1, and trace of this matrix is +2. Sigma V operated on xy contributes chi is equal to 0. For each sigma V, as these belong to same class, the matrix corresponding to these sigma V's are given as -1, 0, 0, 1, 1/2, under root 1/2, minus under root 3/2, minus 1/2, 1/2, under root 3/2, under root 3/2, minus 1/2, sigma V double dash and sigma V dash. Trace in each case is 0. Effect of C3 on xy unit vectors, the matrix for is -1/2, minus under root 3/2, 3/2, minus 1/2, and trace for this is -1. Thus, for xy unit vectors, the effect of symmetry operation E, C3, sigma V gives the character as +2, -1 and 0 respectively, and these characters correspond to E irreducible representation. In C3V point group, these are shown over here. E in the last column, xy or Rx, Ry, Z as the vector. the binary or ternary functions x square, y square, z square, xy, xz, yz, x square minus y square plus y square, x cube as basis for irreducible representation similarly can be worked out by taking the direct product of the basis functions, that is x, y, z as the basic function. We can take the direct product and get the direct product function as the basis. Let us take z square function as the basis and find irreducible representation for C3b point group. Now, let us take the z basis. A1 for this is z unit vectors as the basis, A1 for z unit as a vector. I take the direct product A1 and I get the character for E as 1, C3 as 1, sigma is 1. So, z unit vector gives me z square, and so z square is also the basis for A1 because the character I get by direct product is 1, 1, 1. Now, similarly, other binary and ternary functions can be taken as the basis and corresponding irreducible representations can be worked out. So, in this module, what we have seen, applications of the rules or theorems derived from great orthogonality theorems have been explained. What is a character table of a point group is explained. Various sections, various parts of this character tables have been explained, and character table for each point group is unique. Let whatever be the molecules, if they belong to the same point group, they have the same character table. Notation followed for the irreducible representation of the character table has been explained, and the notation is according to R.S. Mulliken's symbol. Various examples are given and the meaning of these irreducible representations have been explained. Explanation for C3b character table is given in little more detail, and various basis functions have been worked out, that is how they are the basis function for C3b point group. Binary or ternary function as basis for irreducible representation is also explained only in little bit, that is z or z square has been explained.